B.3, general solution for binary bits problem. All right. We just got a special solution when n equals power of 2. Yeah. When n equals 2 to the kth power, so we get a solution 1 plus log base 2 of n. All right, yeah. Now, when we go to the general case, we're not satisfied with the special case. We want to have a general solution. Yeah. Then we guess the general solution should be, we use floor function to make log expression to be an integer. And I also explain why we use the floor function, not ceiling function, right? We check one special value when n equals 3, it tells us we should use the floor function, not ceiling function. All right, so we continue. So let's from there, let's do the remaining work. Yeah. All right, so first, the strategy part. We use an old strategy that is guess and verify approach. And we make that guess, right? We already made that guess. Yeah. So that guess, we feel pretty good. So we're very satisfied with this guess, right? Yeah. All right, but we need to verify it. We have a lot of work we need to do to verify it, to show it is correct. Then we feel very comfortable. So later when we apply this formula, we have no problem. We know it is 100% correct. Yeah. All right, so that's the verification step. We need to start, the big part of the work here. Yeah. We use a powerful mathematical tool. A powerful mathematical tool. Yeah. Another one, yeah. Mathematical induction. I think you know it, right? Yeah. Mathematical induction. At least you heard of it, right? Yeah. In discrete math, you have one chapter completely devoted to mathematical induction. It is pretty hard. Yeah, pretty hard. Yeah. It is extremely powerful. Now we need to use its power. So powerful. Otherwise, how can you prove it, right? It's not easy to prove it. It is a very powerful tool. All right, so let's just do it. When we start, we need to check the base case. Usually, this step very easy. Yeah. So we just quickly, we can verify it. It's correct, right? Yeah. Step number 2, induction assumption. This step, although we do not need to do a lot of work, but we need to make the right assumption, right way for the assumption. Then our key step, step number 3, we have a good chance to make it. Yeah. So step 2, you need to do something really careful. Yeah. Here, let me show. Yeah. Here we assume a of k equals 1 plus floor function of log base 2 of k for k between 1 and n inclusive. This is important. Okay? Yeah, this is important because for the mathematical induction, there are 2 versions. The first version, version 1, relatively weak. Relatively weak. The first version, we only assume k equals that n. This assumption is true. And version number 2, which is a strong version. Yeah. Here we need to use that strong version. Strong version, version number 2. Okay? Yeah. That version, we make more assumption. So when we assume this formula is correct for k between 1 and n inclusive. Assume more. It looks like assume more, but actually these two versions are equivalent. Version 2 gives us more information than version 1, but they are equivalent. So, okay, yeah. So here, let's use the stronger version. All right, yeah. The key step, number 3, when n equals n plus 1, we need to show this formula is correct using our induction assumption. So this is the key formula we need to use again and again, several times. Then we can get step 3. All right, so let's do the work. Proof. For the proof, we need to consider 2 cases, even and odd. Why? It's very easy. Log base 2, right? Log base 2. For even and odd numbers, the behavior when you take log base 2 will be different. So that's why we consider even odd. The first one, when n is odd. When n is odd, let's verify it. All right? When n is odd, n equals 2s minus 1. One way to represent an odd number with s greater or equal to 1. Because we feel it's convenient. You may ask me why we do not use 2s plus 1, not 2n minus 1. Very simple. Because, look at left-hand side, n plus 1, right? We need to represent n plus 1. If you make n to s minus 1, plus 1, minus 1 cancel out. That's very nice, right? Very nice. Yeah. So to use this 2s minus 1, it's a better choice. Yeah. All right, so let's do the simplification. Here, a of n plus 1 equals substitution, variable substitution, a of 2s. 2s, then we apply what? Remember, we have that recurrence relation, right? Yeah. So let me use space here, recurrence relation. A of, not much space. A of n equals a of floor function n over 2 plus 1. Okay? Yeah. I didn't write this formula explicitly, but here we need to use it. Okay? So you plug in n equals 2s. So you have right-hand side, take floor function a of s plus 1. Okay? A of s plus 1. Now, when you calculate a of s, can we use the induction assumption? This is the first time we used induction assumption. Yes, we can, because s is in this range, s. Okay? Yeah. S in that range. So by induction assumption, we have a of s equals floor function of log base 2 of s plus 1 and plus another one, so we have plus 2. Okay? Yeah. Then let's go back to check why we can use this induction assumption. Yeah. Because the range of S represented in n plus 1 over 2, right? That expression can be easily shown between 1 and n. Very easy to see it. You can do some simple calculation if you like, but we can easily check it. Yeah. So that's the reason we can use that induction assumption. All right, so that's the right-hand side. Okay, right-hand side of this equation. Now we try to verify it. Next, we need to do the left-hand side. To do the left-hand side, this is left-hand side. Okay, all right, but to work on this one, it is a little harder than the first step. Than the first part, right-hand side. First, we use the variable substitution, right, using S variable, in this way. 2 times S by a logarithmic property, that 2 times S, we can write 1 plus log base 2 of S, right? Yeah. This 1 is an integer. Inside that floor function, we can take the integer in the floor function out of the floor function. Okay? Yeah. So that formula, like this one, n is any integer inside the floor function, we can take it out. This formula given in the textbook on this page 477, Appendix A. Yeah, a simple formula. Yeah. With this formula, then we simplify the expression of the which side? Right-hand side, right? Yeah, right-hand side. So this is the right-hand side. Okay, right-hand side. Now you can see you compare the left-hand side. So this is the left-hand side. Okay, right-hand side. Same expression. So we complete the verification. Okay. All right. Yeah. Next. Other case, right? Other case. Yeah. So now let's do the other case. Yeah. Still another half of the work. Yeah. Oh, sorry, even case. We did odd case first. So even case. This time n equals 2s. We use the similar way, left-hand side, right-hand side, right? Yeah. Mathematical induction assumption, right? Yeah. All right, so n equals 2s. Left-hand side, a of n plus 1 equals a of 2s plus 1. This time, we need to use that recurrence relation another time. So let me write it again. So we get a of s plus 1. When we take the floor function, that plus 1 is gone, right? Yeah, it's gone. Yeah. So still a of s. So we can apply induction assumption. Although you can check, right? You can check s is in that range. Yeah, easily see that. Okay, yeah. All right, so now finally the right-hand side. Yeah. First, 2s plus 1 inside the parenthesis of the log base 2, but this time, this is the hardest step. The hardest step of this whole proof. Why it is hardest? Because we need to use a special formula. Okay, yeah. So the formula is this. Okay, yeah. Look at this, the formula. All right. Still on page 477, Appendix A. Yeah. So look at that. Yeah. Seeding function, left-hand side. Yeah. Parenthesis n plus 1, right-hand side floor function. Okay. Yeah. Log base 2 of n and a plus 1 outside the floor function. All right, now we use that one to calculate this expression. Okay, yeah. All right. That expression, because we use the floor function, that corresponds to the in the original formula, right-hand side, that term. Okay, so then left-hand side term, we need to use ceiling function, right? And inside parentheses, we need to plus 1. Okay, plus 1 on top of the part in the left-hand side inside the parentheses. So that's 2s plus 2, then minus 1, because this plus 1, when we move to the left-hand side, it becomes minus 1. That manipulation. Okay, so I hope you can get it. Okay, so I skip some intermediate calculation, but I feel you can get it. Yeah. All right, simplification. The 2, we can take it out. We can write 2 times s plus 1, right? So log base 2, the whole thing, right? By a property of logarithm, we take that 2 out of it. That is 1. Yeah. So that 1, because 1 plus this, 1 and minus 1, cancellation, gone. Okay? So the answer is this. Cancellation, it's gone. Okay? But this, look at this form. Ceiling function, right? Yeah, ceiling function. We need to use this formula another time, ceiling function, right? That can be written as the floor function way, yeah, plus 1, okay, plus 1, yeah. All right, but that is just this part, right? Yeah. We have another 1 there, so plus that 1 again, right? Yeah. Then we have this 2. So compare left-hand side, right-hand side, 2. Are they the same? Yes, they are the same, right? Yeah. If they are the same, what's the conclusion we have, right? So the conclusion is the formula we just make that, step 3, we try to show that one is correct. Yeah, so we verify 2 cases, both correct. So the whole formula guess is correct. Okay, now verified. Then, by the mathematical induction, our conclusion is the original. So that formula, we try to show that one is correct. Okay, yeah. So we finish that proof. So this proof is pretty hard because we use several formulas, yeah, and related to the logarithm properties. Yeah. All right, so try your best to understand the proof. Yeah. All right, so let me stop this video and our whole part B lecture.